Okay, so thank you. Okay.
We're going to talk about trigonometric integral of this form, where the integram is some power of tangent x times some power of secant x. Remember the trig identity, 1 plus tangent square equals secant square? Notice here, the exponent on tangent and secant are both even. In this example, again, I want to use the safe method. You see the exponent for secant here is even.
And it's greater than or equal to 2. Okay. And what happened over here, you want to save. I'm going to save a secant square x together with the dx. Why do I want to do this? Because think about which function differentiate give you secant square. Which function when you differentiate give you secant square?
Tangent x.
Tangent x. Okay. So this is the d of tangent x. Now, once you save a secant square over here, the remaining power for the secant over here will be even, still even, right? So you have secant square x over here. Now, what about this tangent? Do I need to do anything to change it? What do you think? Do I need to do anything to change into secant?
No.
No, because this later on is going to become the integral with respect to tangent x, right? So this one over here, you don't want to change it. So let's just keep it. So tangent to the 6th power. You see, because there's tangent x over here, this is tangent x. Okay, so you want to keep it. Okay. What about this one here? You want to express this in terms of tangent, right? So think about this identity. So what would this become? Let's make the identity. I label that as a star, right? So use the star over there. So this become what? Secant square is 1 plus tangent square. So you express that in terms of this. Is it good? Now you see all of them are in terms of tangent x now. The next step will be the next step. You want to let u to be tangent x. This is going to become u to the 6th power times 1 plus u to the 2nd power, and then du. Now it is we're taking the antiderivative of polynomial, right? Okay. So we will multiply them out. Okay, so this becomes u to the 6th plus u to the 8th, and then du. So that will be u to the 7 over 7, u to the 9 over 9, and then adding c. Finally, we want to return back to x. So what is u? Tangent of x, right?
So we don't have to worry about, when we're integrating that, we don't have to worry about the antiderivative of tangent.
Antiderivative of tangent. What do you mean?
I was thinking maybe we'd have to do something like chain rule or like u sub because tangent, like, and do the antiderivative of tangent somewhere.
Yeah, you did use u sub over here. You need u to be tangent x over here.
Oh.
Yeah.
Okay.
So we use u sub. Chain rule is for differentiation. The u sub is actually the corresponding rule in integration. Okay, so we use u sub over here. So now this type of problem, when you have tangent times secant, you just need to think about what to save over here. So because there's identity over here, when the exponent for secant here is even, you want to save a secant square over here, because that way it's going to become d of tangent x. If you just save secant, it's not going to get anywhere because you want to relate to tangent x. So you need to have derivative tangent x is secant square. So you want to save a secant square over here together with the dx. And now this is still even, and then you can use this identity to express that in terms of tangent. Looking at this problem, let's summarize what's the strategy we have done over here. Okay, so when this I put it in the wrong place. Okay, so over here, when the exponent for the secant over here, it is even, okay, and it's greater than or equal to 2, then we use the save method. You think about this identity, right? So 1 plus tangent square equal to secant square. So think about this identity when you involve tangent and secant, okay? All right. So what you do over here is you're trying to save 1 secant square with dx, because later on this is going to become d of tangent x. The derivative of tangent x is secant square, okay? And then by doing this part over here is you still have an even, right? So you still have a secant over here to some even power. Then you're going to use this identity. So you're going to use this identity over here, and you express that in terms of this, in terms of tangent x. Okay, so that was the strategy to deal with this. Okay. Okay. Now the next example here. This time over here, the exponent for secant here is not even. We cannot use the strategy above. This time, the exponent for tangent over here is odd. Think about this identity. We try to make it even, okay? So we're going to save again. Okay, so which one we save? So I'm going to save 1 tangent x with dx. But that is not going to get us anywhere, because which function differentiate give you tangent x? Well, we don't know, right? So, but tangent x has a friend, okay? They always go together. So let's take a friend over here. So I think secant x will be good to go with tangent x, right? So instead of just saving tangent x, I'm going to save 1 secant x over here also, okay? So that way, when you save them together, this is going to become d of what? Which function differentiate gives you secant x times tangent x? SST. Which function differentiate give you secant times tangent?
The regular secant?
Yeah, just regular secant, right? So the derivative of secant is secant times tangent, right? So this is just a regular secant, right? Just a secant x. So that will be this secant x. So that is going to become d of secant x over here, okay? So we save 1 tangent x so then to make the exponent to be even, but that's not enough. We need to save a friend together with the tangent x. So we save a secant x together with the tangent x dx. So that will become d of secant x. Now, after you have done this, so let's see what are the remaining part over here. So this is going to become tangent to the 4 power now, right? To the 4 power x. And then this is going to be secant to the 6 right now, right? 6 power. Now let's think about the next step. This is an integral with respect to secant x now. We want everything in terms of secant x. So do I need to change this? Do I need to do anything with this one? This one, you don't want to change it. That's already in terms of secant x, right? So no change over here. So secant x to the 6th power. We'll just copy it down. Now what about this tangent to the 4 power over here? We want to express that in terms of secant x. So remember this one here, it is the, well, remember Corey just talk about when we have a sign, right? So this is the square of what? It's the square of tangent square, right? So now we will have this is going to become the square of tangent square is what? Secant square minus 1, right? Okay. So we have secant square x minus 1 and then square. Now you see this is secant x, and that's secant x, and that's secant x. They're all in terms of secant x. Now what will be the next step? The next step is to do the u sub. So let u to be this. Then this is going to become u squared minus 1 squared, and then u to the 6th power, right? And then this is the u. All right. Now we just need to expand this. This is u to the 4 power minus 2u squared plus 1 times u to the 6 du. And you multiply this out, distribute u to the 10 minus 2u to the 8 plus u to the 6 du. And then we just integrate that term by term. So that will be u to the 11 over 11 minus 2u to the 9 over 9 plus u to the 7 over 7. And at the end, you add a constant, right? And don't forget to return back to x. So what is u? U is equal to secant x. So this will be secant x. Put this to the 11 power over 11. 2, we have secant x, and then to the 9 power over 9, and then plus secant x, and then to the 7 power over 7, finally adding a constant. That's it. All right, so question. So let's summarize the strategy we use in this example. So this time when we have this exponent for tangent, here's r, we want to make it even. How do we make it even? We want to save one tangent x over here together with the dx. But just saving one tangent x is not enough. We need to save a friend together. So we save secant x over here together with tangent x. Then this is going to become d of what? It's going to become d of secant of x. Then later on, then this part over here, the remaining part here. Okay, maybe I should add something here. Now this becomes tangent to some even power now. After you have done that, right? Okay. So now we express that in terms of secant x. Okay, so summarize this. Now, when you deal with this type of integral, when you have tangent x times secant x, there are two cases that we know how to deal with. One of the cases is when the exponent on secant here is even and greater equal to 2. The other one is when the exponent on tangent is odd. When this is even and greater equal to 2, okay, we're going to do the save method. So what do we save? Do you guys remember? We want to save one
of the tangent, or
we want to remember, we want the exponent here to be remain even. Okay, so we're going to save a secant square. Save one secant square with dx, because that way this is going to become d of tangent of x. The tangent x is secant square. What about this one here? When the exponent for tangent here is odd, remember we try to make it even, right? So we're going to save one tangent x together with dx, but that's not enough. You need to have a friend. So we save a secant x together with that. By doing this, it's going to become d of what?
Secant x?
Yes, d of secant x. And then that's it. Now you might ask, what about other cases? But for other cases, there are no clear-cut guidelines. And sometimes we use either this or this formula to deal with it. So you won't be asked to do those. Now let's play a game over here. Guys ready? A paper. Okay. And they tell me what to do. Okay. So that's good. Okay. When you have this, okay, when the exponent for the sign here is odd, which one to say? Without looking at your note, can you tell me which one to say?
Sign.
Save one sign x together with the dx. Okay. So you could do that. Okay. So what happens when the exponent for cosine here is odd? Which one to save?
Save cosine.
Yeah, we save one cosine x together with dx. So that one is going to become d of sine x, right? Okay, now what happens when you have the tangent times secant? When the exponent for tangent over here is odd? So which one you save? What do you save?
Secant?
Okay, so if you just say secant is not enough.
Secant tangent? Secant times tangent?
Yeah, you save secant times tangent. You got it. Okay, so you secant and tangent together. Okay, so you save a secant times and tangent together, and that's going to become d of secant x. So the last one over here. Okay. So what happens when you have this exponent for secant over here is even and greater equal to? So which one to save?
Secant squared.
Yeah, you save a secant square x together dx. Okay. By doing this, so you save a secant square x with dx, then that is going to become d of tangent x. All right. Okay. What happens when the exponent for sine and cosine are both even? Over here.
The half angle formula.
Half angle formula. See, you guys got it. Good job. Okay, so we use the half angle formula. Okay. All right. Good job. Okay. Okay. I'm going to stop here. That's something very good to hear. Calculus. Yeah. I feel very glad. Happy for you.